We pass to method number 2 to find the partial orders and the partial orders M and N in order to deduce the global order of the reaction. The method number 2 is the ratio technique. As I explained previously, in any experiment in the lab to study the kinetic of a reaction, you obtain a table of 6 columns. Time, column 1 is time, column 2, the concentration of A at time t, the concentration of B at time t, column 3, RA at time t, column 4, RB at time t, column 5, and in column 6 you obtain the rate of the reaction as a function of time. So you obtain sets of data R, A, B, RA, RB, and R. So now we will do experiments, and we will take set from experiment 1, and we will apply the rate law expression, the rate law, and we consider a set in experiment 2, and we apply the rate law expression. Then we make the ratio between the set 1 and set 2 in order to deduce, for example, M, N, or K. So repeat the same experiment at the same time and change the initial concentration of the reactants. Each experiment allows to calculate the rate of the reaction. So we obtain set of data T, AT, BT, RAT, RBT, and R. For each experiment, the expression of the rate law is the same. So we have the same M and N since we have the same reaction. And if these experiments are realized at the same temperature, so we have the same value of K. So in the ratio technique, we repeat experiments of the same reaction at the same temperature. In each experiment, we obtain a table of data T, AT, BT, RAT, RBT, and RT. Then we have to use one set from experiment 1 with one set from experiment 2. Example. Consider the general reaction AA plus BB gives CC plus DD. In experiment 1, start at A1 at initially B1. Experiment 2, A2 and B2. Experiment 3, A3 and B3. The rate law expression can be applied on experiment 1, on experiment 2, and on experiment 3. Since we have the same reaction, so we have the same M and N. And since the temperature of the 3 experiments is the same, so K is the same. Suppose you start initially B1 equal B2. In experiment 1, you use initially B1. In experiment 2, you use concentration of B equal the concentration of B in experiment 1. So B in experiment 1 is B in experiment 2, but A concentration are different. We write the rate law expression. R1 equal KAM 1 times B N1. What is the time I choose in reaction 1? In experiment 1, I choose the time at T equals 0. I also choose the time equal 0 at in experiment 2. I wrote R2 equal KAM times B and 2. Pay attention that M and N are the same. At T equals 0, I use B1 in experiment 1. At T equals 0, I use B2 equal B1 in experiment 1. So I can cancel the concentration of B. K are the same, so I obtain R1 divided by R2 equal the concentration of A1 to the power M, concentration of A2 to the power M. I know R1, I know R2, I know A1, I know A2, so I can calculate M. Now we have to choose a set of experiment 1 and set in experiment 2 where the concentration of A are equal, and we apply the rate law expression, so we eliminate the concentration of A from this equation and we find the value of N. I will consider an example. Determine the rate law expression for the reaction between A, B, and C. So the rate law expression equal KAM BN CP. The following experiment were done. Experiment 1, I start with A0 equal 1, experiment 2, B0 0.1 and 0.1 A0. Student 2 start with A0 0.2, B0 0.1. So student 1 and student 2 start with the same initial concentration of B, different initial concentration of A. Student 3 start with 0.2A, 0.2B. So student 3 use different conditions than student 1 and student 2. And student 4 start with 0.2A and 0.1 B0. We have 4 experiments done by 4 students where we change the initial concentration of A and B and also the concentration of C. So we have A, B, and C concentrations. In the 3 experiments, in the four experiments, each student, the student should obtain a set of data, a table T, AT, BT, CT, RAT, RBT, RCT, and the rate of the reaction. Now I will choose the time equal 0 for the 4 experiments. So I will apply the rate law expression at T equals 0 for the 4 experiments. For student 1, I will write R0 equal 0.1 to the power K times 0.1 to the power M times 0.1 to the power N times 0.1 to the power P. Student 2 will write at T equals 0 R02 equal 0.2 to the power M times 0.1 to the power N times 0.1 to the power P. And student 3, student 4 will apply also the rate law expression at T equals 0. In each experiment, I said we have the value of the rate of the reaction. One of these values obtained of the rate of the reaction in the experiment is the initial rate. So student 1 knows R0, student 2 and student 3 and student 4, they know the rate of the reaction at T equals 0. So I will divide the rate law expression of student 1. On the rate law expression of student 2, I will eliminate the concentration of B and I will eliminate K. I will obtain R01 divided by R02, which are known, equal 0.1 to the power M times 0.2 to the power m. So by this way, if I divide set 1 on set 2, I will obtain the partial order m. Divide. So 1 over 2, I obtain m. Divide 2 over 3. We eliminate A0. We eliminate C0. So we can find the partial order with respect to B. Divide 2 by 4. We eliminate the concentration of A0. We eliminate the concentration of B0. So we can obtain the partial order with respect to C, which is P. So this is a ratio technique where we divide a set obtained in experiment 1 on set obtained on experiment 2 in order to eliminate, for example, one of the reactants A, B, or C. The best time, the best choice in sets of each experiment is the time equals 0. Since at t equals 0, we know directly the initial concentrations. So this is the ratio technique to calculate M, N, and P. Then the global order is equal M plus N plus P. Method number 3. To remember, method number 1 is the log plot. We draw ln R as a function of ln concentration. Method 2 is the ratio technique. We divide set of data obtained in one experiment on the set of data obtained in other experiment in order to eliminate one of the reactants and to keep the concentration of the second reactant, so we can calculate the order, the partial order with respect to this reactant. Method number 3 is the integrated rate law. The integrated rate law, for any reaction of known order, the concentration of the reactant change according to time. For example, I will prove that for a reaction of 0 order, the relation between the concentration and time is given by concentration of A equal minus KT plus A0. If the reaction of A to products is of first order, the relation is ln A equal ln A0 minus KT, and the reaction in second order, the relation will be 1 over A equal 1 over A0 plus KT. I will prove this relation later. Okay. So how to know the order of the reaction? In any kinetic experiment, you have a table where you have the variation of A as a function of time t, as for example, you studied in the college. You have a table, concentration of A as a function of t. If this relation is proved, that means your reaction is 0 order. If not, you pass to the second relation, ln A equal minus KT plus ln A0. If you can prove that this relation is justified, so your reaction is of first order. If not, you pass to relation number 3, 1 over A equal KT plus 1 over A0. And if you justify your relation, that means the reaction is second order. So now how to justify one of these formulas? You have a table from your experiment. You have a table the variation of A as a function of the time t. Draw A as a function of time t. If you obtain a straight line, this is the equation of straight line, y equal ax plus b. If you draw concentration of A as a function of time t and you obtain a straight line, so this formula is justified, and therefore you can deduce that your reaction is zero order. If not, transform the column A as a function of t to len A as a function of t. Add a column len A and draw len A as a function of the time t. This is the equation of straight line. Len A as a function of t, y equal ax plus b. If you can prove that the variation len A as a function of time t is a straight line, you stop and you deduce that your reaction is of first order. If not, draw 1 over A as a function of time t. If you obtain a straight line, this is the equation of straight line, 1 over A, y equal ax plus b. If you obtain 1 over A as a function of time t is a straight line, so you can deduce that your reaction is of second order. So what is the integrated rate law? You have in any experiment, kinetic experiment, you obtain the concentration, the variation of the reactant A as a function of time t. Draw first A equal ft. If you obtain a straight line, you stop and you say that your reaction is zero order. If not, draw len A as a function of t. If you obtain exactly a straight line, you stop. You say your reaction is first order. If not, draw 1 over A as a function of t, and in your curriculum you should obtain a straight line. If the reaction is not zero order or not first order, it should be second order, but you have to prove it. So you draw 1 over A as a function of t, and if you obtain a straight line, the reaction is second order. This is the method number 3, the integrated rate law, or in other words, the use of the formula of the variation of the concentration as a function of time in order to deduce the order of the reaction. I will prove the relation for order 0. In your curriculum, in the first year, I will consider only the type of reaction where you have one reactant A transformed to products. So you have one type of reaction studied, not A plus B to product. Only the integrated rate law will be proved for the reaction A to products. Suppose this reaction is zero order. That means R equal K concentration of A to the power M and M equals 0. A to the power 0 is 1, so the rate of the reaction is equal K is constant. In the previous parts, when I talk about the rate of the reaction, I mentioned that the rate of the reaction decreases with time, or the rate of the reaction is constant with time, but never the rate of the reaction increase with time. R equal K, that means the rate of the reaction is constant, independent of time. So the reaction of order 0, the rate of the reaction is constant. R equal K. And how to deduce R from RA? R, according to the stoichiometry, RA divided by 1 is equal to R, and RA is equal minus the concentration of A divided by dt. So this expression R equal K can be written RA equal K. So R equal minus dA divided by dt, which is RA equal K. So minus dA equal minus K dt. Integral of dA from the initial concentration A0 to AT equal minus K integral of dt from the initial time 0 to the time t. So A t minus A0 equal minus KT. This relation is obtained when we suppose that our reaction is zero order. So if the reaction is zero order global, the variation of A as a function of time is given by AT minus A0 minus KT. That means if you draw AT as a function of the time t, you should obtain a straight line, and the slope of the line is equal to minus K. In your problem, you have a table where you have the variation of A as a function of the time t. Draw AT as a function of the time t. Suppose you did not obtain a straight line. That means this relation is not justified. If this relation is not justified, so what you propose from the beginning is incorrect. That means your reaction is not zero order. And if you draw the variation of A as a function of time t, and you obtain exactly a straight line, so this relation is justified, so what you propose is correct. As a conclusion, I have the variation of A as a function of t. I want to know the order of this reaction. First, I draw the concentration of A as a function of time t. If I obtain a straight line, so my reaction is zero order or has a global order equal to 0. What is the relation between the concentration and the time t for the reaction supposed of first order? By the same analogy, consider the reaction A2 products. Suppose the reaction is of first order, so the rate law expression R equal Ka to the power 1. R equal Ra according to the stoichiometry. So R equal Ra and Ra equal minus dA divided by dt. So R equal minus dA divided by dt, which is Ra equal Ka. So dA, the variation of the concentration of A, equal minus Ka dt. That means dA divided by the concentration of A equal minus K dt. Now we will do the integration of the two parts of the equation. Integral of dA divided by A from the initial concentration A0 to the final concentration AT equal minus K outside the integral, since K is constant, from the time t equals 0 to the time t dt. The integration dA divided by A is ln A, so we obtain ln AT minus ln A0 equal minus KT, or ln AT equal ln A0 equal ln A0 minus KT. Now we draw. Suppose we draw first A as a function of time, and we did not obtain a straight line, so the reaction is not zero order. We suppose now that our reaction is first order. We draw ln A as a function of time. Ln A as a function of time. If we obtain a straight line, So this straight line, the slope of the line is equal minus k. So this relation is justified. That means what we propose from the beginning is correct. So our reaction is first order. Suppose that the variation len A as a function of time t is not a straight line, like this curve. So our reaction is not first order. We have to pass to the equation of the second order. Suppose the reaction from A to product is second order reaction. That means the rate law expression is given by R equal Ka square. Instead of R, we will put Ra, since the rate of the reaction is directly related to Ra. R divided by 1 equal Ra divided by 1. So R equal Ra minus dA divided by dt equal Ka square. So dA equal minus Ka square dt, dA divided by A square equal minus K dt. Now we will do the integration on the two parts of the equation. Integral of dA divided by A square from initial concentration A to the final concentration At equal minus K integral from the initial time 0 to the time t dt. So we obtain the relation 1 over At minus 1 over A0 equal Kt. So 1 over At equal 1 over A0 plus Kt. If we draw 1 over A as a function of the time t and we obtain a straight line, the slope of the line is k. So this relation is justified and our reaction is of second order. Example. Consider the following reaction. We did an experiment in the lab and we calculated the variation of C4H9Cl as a function of time. So we have the concentration of A as a function of time. The question, find the order of the reaction. First, I will draw the concentration of C4H9Cl as a function of time. Draw concentration C4H9Cl as a function of time, and the variation is a decreasing curve. I did not obtain a straight line. So the relation At equal A0 minus Kt is not justified. So this reaction is not of zero order. Now I will pass to the second proposal. Suppose the reaction is of first order. I will transform the curve. I will add a column where I transform C4H9Cl to len C4H9Cl, and now I will draw the len concentration C4H9Cl as a function of time. I obtain a straight line, exactly a straight line. We obtain exactly a straight line. So the variation len At equal len A0 minus Kt is justified. So the reaction is of order 1 and the slope of the line is equal to minus k. The slope is equal to minus k, so k equal 2 times 10 to the power minus 3. Second, minus 1, I will talk about the unit of k later. I will talk about the unit of k according to the order of the reaction. So now we stop. It's not necessary to draw 1 over A as a function of time, since we proved that this reaction is of first order. So for the reaction of order 0, the variation of A as a function of time is a straight line. For reaction of order 1, the variation of A, as a function of time is not a straight line. Suppose the reaction is 0 order. So the variation of AT as a function of time is a straight line. The variation for reaction of order 1, the variation of ln A as a function of time is a straight line. But the variation of A as a function of time for reaction of order 1 is a curve. For reaction of order 2, 1 over A as a function of time is a straight line, but A as a function of time is a curve. So this is the variation of A as a function of time for reaction of order 1 and order 2, and all the reactions you studied in grade 12 are reactions of first and second order, since the variation of A as a function of time is a curve. The variation of A as a function of time is a straight line only for the reaction of 0 order.